And these are my unindicted co-conspirators from several institutions here. A rough outline. I'm going to talk about molecules in diffuse clouds. I'm going to talk about using HCO plus to trace H2 and explain Isabelle Grenier's dark neutral material. And then talk a bit about the complexity, the physical complexity of conditions on diffuse cloud sightlines, excitation, physical conditions. So there are now quite a few molecules that exist in diffuse clouds, are known to exist in diffuse clouds. And this is a timeline broken down by wave bands. So early on, there were these diatomic molecules, some very important ones, of course, H2, HD, OH, and eventually these were found in the radio. In the 80s, there was very little discovery of molecules in diffuse gas, but Pierre Cox published the detection of C3H2 along a line of sight, and that was a harbinger of things to come, because slightly later, Robert Lucas and I, using NOEMA, or the predecessor PDBI, discovered quite a few molecules in millimeter wavelengths toward diffuse clouds, and I'll explain what we really mean by diffuse clouds in a moment. But it became evident that these small molecules here were just the smallest members of larger species. And although there were many papers explaining these species back in the day, there's very little theory behind the larger members of the families of which they are part, and which are very heavily correlated and which vary together in these species. H2CO and H3 were realized in diffuse clouds by Anna Nash, a Churchwell student. There was something of a relâche in the aughts. I think only one molecule was discovered in the radio. It picked up again with a sweep at the 30-meter. And I'll show a few recent results from a sweep of the 40-meter Yebes telescope, where we've, at Q-band, been given the opportunity by a flaring of BLAC and the availability of telescope time, thank you, Pepe and Elaine, to discover quite a few astonishing molecules in this gas. So what do you mean by diffuse gas? Well, here's a picture of a region of the sky with the positions of a few background sources, quasars outlined. And for instance, 2145 plus 067, the reddening is only 0.08 of a magnitude. But in fact, when I show you their shadow and absorption lines, there's some H1, and then there's an HCO plus line. There's no CO emission at very low levels, but the HCO plus comes up. And you see that the HCO plus is somewhat eccentric in the H1 line. It's not in the strongest or deepest, widest component. And when you think about it, right, the molecules like energy, they like warmer regions, they need to be formed. The H1 has an inverse temperature dependence, right? So it likes cold gas. And the H2 and the H1 are competing for the same nuclei. So they can't both be occupying all the gas at the same time. If you go to a slightly higher extinction, this is 3C454.3, you find saturated lines already, you find HCN, you find dense gas tracers at reddenings that are very, very small. You go to BLAC, which is one magnitude of extinction, in which I'll show you later, many, many more spectra, and the lines are heavily saturated. You see formaldehyde, you see ammonia, you see lots of things that I'll show you in a moment at one magnitude, not near a dark cloud. This is not the envelope of a dark cloud. It's a freestanding region in space. One magnitude, you see this stuff. So, the trace molecules appear almost as soon as H2 appears. The abundances are surprisingly similar in many cases to TMC1. There are some surprisingly large molecules even at one magnitude. And what I didn't show you, but I will allude to later, is that along this line of sight, where obviously the reddening is quite high, when you observe a line of sight like that, you often find that it's just a superposition of many diffuse clouds individually. Well, there are some surprisingly complex species at AB equals 1 magnitude. Here's methyl cyanide toward BLAC, found with the BLA at K-band, or well, lower Q band. You know, it's not surprising to find something like HC3N perhaps toward one of these sources that's got AB of 4 magnitudes, but to find methyl cyanide at 1 magnitude, I think is rather surprising. Now, most recently, during some test observing at the 40 meter, BLAC flared over 10 Janskis to the point where it was notably affecting increasing the system temperature, which is good for observing absorption lines. And we found C2S and acetaldehyde, and in fact, other species that were alluded to, that were shown on the previous slide. So I'm not going to discuss really the chemistry of complex molecules in diffuse clouds because it's not a well understood subject. I'll get back to it in the last slide of the talk. But these things exist at 1 magnitude, and we're still discovering, you know, others. Well, okay, so, you know, what are these things good for? You know, there's the intellectual problem of discovering why these molecules exist, but you also want what you're doing to be useful for other people. Otherwise, you know, they may not read your papers. So HCO plus absorption, I think, has been the most useful. It's ubiquitous. It's very easily observable because of its high dipole moment. It turns out that it seems to trace H2 with a more or less constant abundance, and I'll give you an example of that in a moment. It explains CO chemically if you drop it into a self-consistent model just by the thermal recombination at the temperature of the cloud. It's detectable when CO emission isn't. I showed you an example of that. And in fact, it's something that should be used to constrain models of the ISM. So as an example, here's 46 directions that were studied in HCO absorption with Marivon and Isabelle Grenier, okay, who actually is, you know, the discoverer or inventor of the dark neutral medium. It's the stuff that's left over when you try to account for all the material that should be there by looking at the H1 that you can see and the CO that you may or may not be able to see. And it's the stuff that is inferred to be there from Planck, Fermi, from column density measurements of other tracers that you just can't find. Well, anyway, there are 46 directions that we studied, and here are some of them shown against reddening in the outer galaxy and against CO in chameleon. So of the 13 directions that we studied in chameleon, only one of them had CO, but in fact, every one of them has HCO plus. So it's a rich thing to study. Now here, what I'm going to do is abstract those 46 directions and show you column densities versus reddening for different species, okay? So here's the H1 of the 46 clouds binned, okay, to get the statistics to appear like this. And right off, you see that although the reddening differs by a factor of 12, the H1 total line of reddening, the total H1 varies by a factor of 3. So you know something else is going on here. The H1 is not representing the total column. Now, Isabelle decomposed the H1 into the components that were extraneous and those that were directly associated with the clouds that we're observing. And that varies very little at all, right? It's even a stronger suggestion that something else is happening. And indeed, her dark neutral medium, right? This is the gas that was missing. Looks like this. The dark neutral medium varies by about a factor of 100 from down here to up here, from nothing at very low H1, at very low reddening, where obviously the H1 is showing you all of the gas. There is no DNM, right? Varying across here, increasing the DNM to the point where the DNM contains as much material as the atomic hydrogen does, and then falling at the highest reddening, where finally CO turns on and accounts for the molecular hydrogen, which is stealing nuclei from the H1. So now I'm going to superimpose on that the H2 inferred from HCO plus, right? It's the green compared with the blue. The blue is the DNM. Okay, great. And you can see that the H2, right, increases following the D&M, but not falling, where in fact the material becomes predominantly molecular. So it does trace. Okay, well, excitation is notoriously difficult to derive from absorption lines. But in fact, when you are given enough telescope time that you can actually find the weak emission from species like HCO plus and HCN, it's constantly there at about 1% of CO, right? So these dense gas tracers are actually present in diffuse clouds at these levels, even though they have extremely small excitation temperatures. The point is that in a diffuse gas where there's no de-excitation, all of the energy that's put into the line eventually comes out, and the emission is extremely efficient because it's not being used to prop up the molecules in higher excitation levels. So in fact, for diffuse gas, there's no critical column, there's no critical density of the molecule. The emission is not dependent on the A coefficient of the molecule. Okay, and there's a paper showing this. Now, the question then becomes, what do you learn of the physics of these clouds by studying diffuse gas? So here's a line of sight at low galactic latitude, which has very high extinction because it has 5 lines, each of which look like about half of BLAC. So you add 5 of these and you get a fairly substantial extinction along the line of sight. And it has C2H. But look what happened when you look in formaldehyde. Well, there's chemical differentiation, right? All of these things that have roughly the same amount of HCO plus have very different H2CO, and they have very different CS. And this is all the old stuff. But here's some new stuff. Here's a much higher signal to noise spectrum in CS that we took, that Mary Vaughan took in a 2 millimeter sweep at ERAM. But what happens when you look at formaldehyde? Oops, right? Although there were 2 lines and you thought that they were the same as the CS in formaldehyde, well, they reappear when you actually study the same molecule at 2 millimeters. So there's a confusion here between abundance and excitation. So what was going on? The high optical depth ratio, 3 to 2 to 2 to 1, implied very high density, not something that we expect along a diffuse cloud line of sight, where 5 clouds all appeared identical in HCO+. The high density made us think about the ionization fraction. Electron excitation has always been believed to suppress anomalous 6 centimeter formaldehyde absorption, but the rates had never been computed. So Mary Vaughan approached Alexander, and he produced these rates so fast that either he did them in his head or he had them in his back pocket. There's just no other explanation for how quickly we came up with these. But what we found was that anomalous 6 centimeter absorption, in fact, requires a very small electron density. So that when you see 6 centimeter absorption, you're looking at a gas in which the carbon is no longer fully ionized, as you expect in a diffuse gas. The carbon has recombined to something, and you know actually from CO absorption measurements that isn't CO. It's carbon 1. So you've actually traced the first step of the carbon recombination to C1. And another thing is that the 6 centimeter absorption can be quenched in many cases. So chemically, it's possible to understand, in terms of the excitation, it's possible to understand what we saw toward BLAC and the differentiations between formaldehyde species observed at 6 centimeters and 2 millimeters. So, well, okay, so what did we learn? Features without 6 centimeter lines are diffuse. The electron fraction is high. It's consistent with low densities. Well, low density. What's low density when you're observing H2 at 10 per cubic centimeter in the infrared? Features with 6 centimeter and high CS turned out to have high density, low electron density. The carbon must have been largely recombined to CO. But, you know, to actually infer these physical properties along the line of sight required very, very extensive observations. It's hard to determine the physical conditions in diffuse gas. I'm going to close with some old observations that Jerome and I did of the same line of sight back, 15 years ago, in which we actually traced the turbulence in this. Okay, so look at what the CO is doing. This is CO emission, right? Along these strips, one strip, another strip. It's wriggling in and out. And, this is a pattern that you see on all scales in the interstellar medium, the inherent turbulence. Well, okay, so that's it from me. Time went by way too quickly. What's next? Well, we're doing the detections and the abundances from the 40-meter sweep. A 70 to 80 gigahertz sweep at ARM was much less revealing. We're trying to work on the characterization of physical conditions. It's very, very hard. What you've just seen is that really finding the H2 in the HCO plus isn't enough, because there's enormous scatter in the properties of these diffuse gas molecules at the same H2. And really it gets down to a question that Alex Dalgarno surmised when he summarized one of the early astrochemistry meetings at Asilomar in 2005. He said, as a way of dismissing the problem, that everything would be okay as soon as we knew how to do the dynamics. But we're doing increasingly sophisticated dynamic simulations, and the HCO plus still isn't popping out of them by default. So we still have a long way to go, and the chemistry is indeed interesting. So thank you very much.